This is a climate model. It's actually a joint NSF-DOE climate model, which might not exist in the future, but this is it's an animation of water vapor in the atmosphere. So you can see a lot of things that you might expect about the real world. You can see that in the tropics there's more water vapor than at the poles. You can see these atmospheric rivers of water vapor kind of spiraling off the tropical jets. You can see these tropical cyclones spinning around each other. You know, that one's just about to hit Newfoundland. Oof, okay. And you can see a lot of dynamism. Right? The real world also has this dynamism. It also has these complex features that are emergent properties from all of the small-scale things that we can understand and go and measure. And trying to work out how those things, how those processes all interact to produce this kind of picture is really the heart of the work that I do. And I'm going to try and give you a sense for how that works and why we think these kind of simulations have credibility in helping us understand something about the real world. So, what are climate models good for, is the question. You're all supposed to yell out something at this point. What are climate models good for? Okay. So this is good. This means that I can help you answer that question. In a more skeptical audience, you'd all have shouted out, absolutely nothing. But I can see that you're an open-minded and scientifically attuned group of people. So what are we doing? We lived here this winter, right? We lived underneath that big blue spot. This is the winter anomaly of temperatures from our analysis of weather stations and sea surface temperatures around the world for last winter, December, January, February. It was the third warmest winter in the record. The subsequent 3 months, January, February, March, have been the warmest January, February, March in the record. 2014 was the warmest year in our record. And yet we lived there, right underneath the only really big blue spot on that whole map, which was rather unfortunate. But of course, people living in California or in Alaska saw a very, very different winter that is was warmer than you might expect from the trends. The trends that you see over a much longer period, about 115 years here, 116 years, are much more even. You see this warming, particularly in the high latitudes in the Arctic region. You see more warming over the land than over the ocean. You see more warming in the north than in the south. There's a very interesting and perhaps climatically important blue spot in just south of Greenland, but pretty much everywhere else in the world is warming. And so that's an interesting phenomenon, what's going on. If you look at that in the global mean, you get pictures like this. I'm sure you must have seen something like this. So each of these years, each of these dots is a single year, and you can see there's a lot of year-to-year variability. But you can also see that if you go back as far as the late 19th century, and you see where we are today, 2014 is the last dot on that map there. You can see there's been a pretty rapid rise in temperatures. It's not been completely smooth. There was a period there in the 1940s, 1970s when things didn't seem to move very much. But since the 1970s, things have been warming. And then, like right at the last 5 or 10 years, it looks like it's flattened out a little bit again. But you can see that that's not terribly unusual compared to the uncertainty or compared to the variance in those measures. But what does this mean? What does this mean? Look at this. This is about 1 degree Celsius, 1.8 degrees Fahrenheit, beginning to the top. Is that big? Is that important? Does it matter? Those are open questions, right? It's not just because we can measure something, it doesn't mean it matters. So the planet has definitely warmed, but does it matter? Is this scale of warming of the planet something that we need to be concerned with? What causes it? What does it imply for the future? Those are kind of the questions I'm going to try and answer for you today. So does the planet notice these kind of temperature changes? The answer is yes. You can go pretty much anywhere in the world where there is significant amounts of ice and find old photographs or paintings of where the ice used to be. So for instance, this is the Mendenhall Glacier in Alaska in the 19th century. And you can see this is the glacier terminus and the mountains in the background. You can go to that exact same spot today, and it looks like this. Right? And I can do that pretty much anywhere in the world. I can go to the Rockies, I can go to the Andes, I can go to the Himalayas, I can go to Africa, I can go to Papua New Guinea. I don't know if you knew that there were glaciers in Papua New Guinea. Does anyone know that? Well, they won't be there for long. So you can go to the Alps, you can go to Greenland, you can go to Antarctica, or most of Antarctica. And you can see the same thing. So the planet notices these things. Ice sheets, ice shelves, glaciers, they integrate a lot of information. They don't change every year, but they do integrate the information over decades and longer. So they're not the only parts of the planet that integrate over those kind of timescales. The oceans integrate over those kind of timescales. Ecosystems, forests integrate over those kind of timescales. And all of those elements have noticed that the planet has warmed by about 1 degree. Now, why work on models? Why not just work on observations? Right? So the real answer to that is kind of encapsulated in this quote. And it comes from a response that 2 scientists had to somebody who asked them, why don't you just work on observations? And they say, well, if we had observations of the future, we obviously would trust them more than the models. But unfortunately, observations of the future are not available at this time. And that really encapsulates what we're doing. We're talking about prediction. Science is about predicting things that we don't know and then seeing whether our understanding is correct. The biggest unknown is what's going to happen in the future. And so if we want to understand what happens in the future, or what might happen, or what's plausibly going to happen in the future, we really need to work on models. And not only do we need to work on models, we need to evaluate them very, very carefully so that their projections have more credibility than just sticking your finger in the air and hoping for the best. This is a climate model. Some of you might recognize it. But you're all too young for this. This is a punch card. This was actually one of the original GIST models that we had. We had a big AMDAL on the second floor, just above the restaurant. It took the entire floor, had 2 full-time technicians, an enormous electricity bill, and you have more computing power in your watch than we had in that thing. Each of these colored bands is a separate subroutine. This is one line in that subroutine. This is part of the radiation code, and you can imagine that commenting the code was a bit of a chore at that point. So I have no idea what any of this code does. You'll be pleased to know that we no longer use punch cards, but we still use Fortran, which is the language that we wrote that in. Fortran has evolved a little bit since then, but we have about 700,000 lines of legacy code which work and work well, and so we're not going to dump that for JavaScript anytime soon. So there you are, an old climate model. This is an old climate modeler. Some of you might recognize him. Gary Russell, who was the real architect of the GIST model, and is still working on the current versions that we have now. But all of the good ideas that we have in our model, they originated with him 30, 40 years ago. And this is the printout that we used to have of all the results and the code. One of the older scientists was so used to looking at the results on these big kind of computer printouts, we had to buy a specialty, like old-style computer line printer just to keep him happy until he retired, and it cost us about $10,000 just to keep up with the old technology. So how do we build a computer model? So we do it process by process. So let me give you an example. So this is a picture of sea ice flying over the Arctic. And so each of those little dark patches there, that's a lead between ice flows. We can go and we can look at what's going on with that ice. How much of the light from the sun is being reflected? How much melting there is at the surface? How much melting there is from the bottom? How much formation there is in the leads? We can go and measure all of these different processes, and we can encapsulate them. We can calculate what the physics is. We can look at the composition of the ice. We can look at how salty it is, how warm it is, how cold it is. And we can put that all into one little section and say, okay, well, this is what's going on with the ice. And that's one part of the model. Then we can say, well, what's happening with the clouds? How do you form a cloud? We can go and measure that. We can try and see, what are the humidity thresholds that you need to form a cloud over a reasonable area? What happens when there's convection? What happens when there's aerosols and not aerosols? We can put all of those things together. And then we can measure how the light reflects off the cloud, how long-wave radiation from the surface is absorbed and re-radiated by the cloud. We can look at all of these different processes one by one. And then we can put all these pieces together. And so we end up with a jigsaw, right? So each piece kind of connects to the other pieces. And eventually, you have something that looks like it's a real planet. But it's not complete. Ooh, that went too far, damn. It's not complete, right? We don't know everything about the system, right? There are things that we know that we don't understand, right, our known unknowns, and there are things that we don't know, right? So our unknown unknowns. And we're always conscious that those exist. One of the classic examples, of course, in Earth system modeling was the polar ozone hole. So if you remember back to the early 80s, the chemistry models that were projecting the decline of the ozone layer because of the increase in CFCs and other ozone-destroying chemicals said, well, we're going to have a problem here. The ozone layer is going to thin. It's going to get worse and worse and worse and worse. But none of those models predicted that there would be an ozone hole in Antarctica. And so when that data first came in, it was rejected by the satellites that measured it because it couldn't possibly be true. It was only when it was verified by observationalists on the ground who said, no, there really is a hole in the ozone layer above Antarctica, that people went back and said, oh, no, it's been happening for a while, and there's obviously something else going on there. And so once people worked out what was going on, which was a special kind of heterogeneous chemistry on particles, on polar stratospheric clouds, people put that into the model, and then now we can hindcast the existence of that ozone hole. But nobody predicted it ahead of time, right? Because nobody understood what that chemistry was or why that would be triggered. So when we're going forward in time, we know that there are unknown unknowns, right? We know that we do not know everything. And that underlines all of the statements that I'm going to make subsequent to this one. So the models are not perfect, right? Even for something where we think we know the answer quite well, right? The surface temperature near the surface, where else would it be? We can still see that there are significant biases. Down here on the coast of South America, or on the coast of Africa, or even in the whole of the Southern Ocean, right? There are significant biases to our modeling of the system, even though we know what the temperature is, we know what's going on, but we still can't get everything right. And so the question that we have to ask ourselves is not whether the models are right. They're not right. They're always wrong, right? They're always approximations. They're always incomplete. But the question that we have to ask ourselves is whether they are useful, right? So let me define that in a more systematic way. So what I'm talking about is model skill, right? And so what is a skillful model? Well, a skillful model is one that tells us something that we wouldn't have been able to get right if we hadn't used it. And if you think about that, that's a much lower bar than being perfect, which is good, right? Otherwise, we'd never be able to do anything. So there are some models that are extremely skillful. Quantum mechanics is a model of the real world at the microscopic and quantum level that is extremely accurate and extremely skillful. Okay, so climate models are not as skillful as quantum mechanics. But they're far more skillful than economic models, for instance. Okay, that's a low bar as well, I realize. So how do we demonstrate skill? How do we calculate skill? How do we think that we can apply what we learn about the model skill to something that's going to be useful for the future? So we take natural experiments that the world has performed for us, and we see what's going on. So for instance, after a big volcano, so some of you might have seen the imagery from the volcano in Chile last week, right? There was this absolutely beautiful ash cloud that went up to the lower stratosphere, about 14 kilometers, deposited a huge amount of ash everywhere, and a small amount of sulfur dioxide. Back in 1991, there was a much bigger volcano, Mount Pinatubo in the Philippines, and much closer to the equator, which turns out to be important, that puts into the stratosphere a much, much larger amount of sulfur dioxide. Some of you here work on aerosols. What happens to sulfur dioxide, which is a gas, is that it oxidizes and joins up with water and becomes sulfuric acid. Those sulfuric acid particles condense, and they're white, effectively. So when the sun comes in, and there's a lot of these particles, the sunlight reflects, and it actually cools the planet by a significant amount. So the aerosol optical depth, that's a measure of how many of these particles there are in the stratosphere, increased very, very quickly in June 1991, kind of peaked around the beginning of 1992, and then kind of tailed off very slowly to 94, 95. It tails off very slowly because the stratosphere is above the weather. Right? There's no rain, there's no clouds to wash out any of these particles, and so the particles just kind of drift with the main circulation until they settle after a couple of years in the stratosphere. So while they're there, they're cooling the planet the entire time. So we can try and see whether the models themselves can do this same thing. So we can put this into the model. Well, here, model, have some aerosols. What are you going to do? Well, one of the things that happens is that the radiation imbalance at the top of the atmosphere becomes negative. So that means that there's more energy leaving the planet than is coming in, right? Because that sunlight is reflecting off those particles and then going back out to space, which means that there's less energy coming into the system than you would have had otherwise, right? So that means you have a negative radiative imbalance, and what you might imagine as that goes down, that if you have less energy coming in, the planet is going to get colder. But how much colder? Right? So this is the temperature record for that time period. So here was the base climate that we had. This is slightly smooth to make it a little bit more recognizable. And then here is the dip that you see in the subsequent couple of years. So this dip is about 0.4, 0.5 of a degree, roughly, in the global mean on a seasonal basis. And these colored lines behind it are what the models suggested would have happened had you put in this amount of aerosols. And so what you have is a test of the radiation scheme in the models, the surface temperature response of the models, which is a complicated emergent property of the models, and you actually have an evaluation because you didn't know what was going to happen ahead of time. In fact, when this eruption first went off in June 1991, my predecessors ran this climate model instantly with the estimates of how much sulfur dioxide there was going to be. And they published their results for what was going to happen in October of that year. So they published their result then and predicted this almost exactly. And that's a real forward prediction. This is a hindcast, so you might say, well, we fixed it. But we didn't. This actually is just, it comes out of the basic equations that we've put into the model. So the models can respond appropriately to a negative forcing to produce a global cooling. But they don't just respond in a radiative sense or just in temperature. They also respond dynamically, right? You saw the pictures that we had, like the animation I had. The big issue, the big advantage of doing this modeling is this is dynamic, right? You can get the structures, you can get the low pressure systems, you can get the storms. And you can get the changes in the winds. And it turns out that even while the globe cools as a function of these big volcanic eruptions, in the winter time, following the northern hemisphere winter, following an eruption, you often get a pattern like this, where you get warming in northern Europe and warming in kind of mid-North America, and then a big cooling over Labrador and Greenland. And this is a dynamic pattern. It's because the winds have shifted in response to the changes in temperature in the stratosphere and below. And so the model also produces that same dynamic change as a function of those changes in the temperature profiles. So what we end up with is a way of testing whether the radiation in the model is okay, whether the surface temperature response is okay, whether the response of the winds to temperature gradient changes is also okay. And we can go through all of these different examples and convince ourselves, if you want to be convinced, that the models don't do a terrible, terrible job. So let me show you another animation. This is a high-resolution animation just for a year from GMAO, which is our sister organization in Maryland. And this is an animation of their model, and it's all of the different aerosol particles are colored. So this orange aerosol here, that's dust that's being picked up from the Sahara and swept across the Atlantic. This blue up here is sea salt that's being swept up by storms in the North Atlantic. This wispy white stuff is sulfates, again from sulfur dioxide, but near the surface, so it's kind of carried with the weather. And there's obviously a big part of the pollution in China, and you can see all those white aerosols there. The green aerosol is carbon, organic carbon and black carbon that comes predominantly from all these red dots, which are fires that are both natural and human set. And you can see how all of these things intersect. Anything that you can see here is having an impact on the climate because it's interfering with the radiation traveling through the atmosphere, it's interfering with clouds, and it interferes with precipitation. All of these aerosols around the Southern Ocean are impacting the clouds are impacting the aerosols, and all of them are impacting both how the circulation around Antarctica is changing because of the ozone hole that I just mentioned, how that's affecting the ocean currents. And if you look carefully here, there's another volcano that goes off just north of Madagascar. Poof, there's another volcano. We can import all of these things into these models now. And we don't do it just to make pretty animations. And I have to say, this is one of the prettiest animations that I've ever seen of a climate model. I use it all the time now, even though it's not mine. But we use it because all of these things intersect. The questions that we want to ask of the models of the real world are how these things intersect. What happens if we change the amount of pollution in the atmosphere? What's that going to do to clouds, to climate, to the circulation? What happens to all of the things that we're doing with fires? How does that change the atmospheric composition? So let me try and answer the question I posed at the beginning. What are models good for? So, conceptual frameworks. Okay, that sounds a bit arty-farty. I mentioned radiative forcing and the radiative imbalance when a big volcano went off, right? The whole concept that allows us to think about different drivers of climate change and their radiative forcing is a concept that comes from modeling, right? Carbon dioxide, greenhouse gases, what does that do? That changes the amount of long-wave radiation that's absorbed in the atmosphere. So if I just change greenhouse gases suddenly, then the total amount of radiation going out the top of the atmosphere reduces. And so that's a positive imbalance. There's more energy coming into the system than is leaving. Just as like in the volcanoes, it was the other way around. That was a negative forcing. We can put those things together, and we can compare the impacts of greenhouse gases and aerosols and deforestation and the ozone hole. And all of these things can be put on the same footing. The conceptual framework that allows that to happen comes from climate models. I showed you an example of hindcasting, going back into the past to see if we can understand the variance that we've already seen in the record. Attributing those changes to particular drivers is a fundamental part of what modeling allows you to do. Without models, you can't have an attribution because you need to have the counterfactual, the what if this didn't happen. What if there wasn't an ozone hole? What would have happened to the winds around Antarctica? What if there wasn't a volcanic injection of aerosols into the stratosphere? What would have happened to the temperature? Only then can you calculate what difference any one of those aspects had. That's a very important role. More kind of interestingly, models allow us to quantify what we're doing. You know, there are more theories for climate change than there are people in the room, and if this was a room full of climate scientists, there'd be 10 times as many theories of climate change as there are climate scientists. But not all theories are created equal, right? Not all great back-of-the-envelope calculations or hand-waving arguments actually make any sense once you start to look at the numbers. And so you have to be able to quantify these things, and models provide the way to quantify your theory of climate change. So we are ecumenical about theories of climate change. You have a theory, we are totally happy to test it out. If you think it's being caused by space aliens from the planet Europa, we will help you test that out. That might be a little bit more challenging than changing the amount of greenhouse gases in the model, but you know, we can work with you. We can generate hypotheses. There's a lot of behavior in these models that people only see when they really dive deep into the diagnostics. And sometimes that gives them a clue for something to go and look for in the real world that might actually be very enlightening. And that's happened many, many times. And of course, prediction, right? Science is about understanding, codifying, predicting to check whether you've understood something for real. And without models, you can't do that. So here's an example of some hindcasts. So this is basically what's happened over the last 100 or so years. So this is this thing that I talked about, the radiative forcing. This green line is the radiative forcing that has occurred because of the increases in greenhouse gases, carbon dioxide, methane, nitrous oxide, CFCs. As you can see, it's been growing since the 19th century. It had a bit of a plateau near the Second World War, but since the 1950s has been growing quite steadily and continues to grow quite steadily. These spikes here, those are the volcanoes. Every time there's a really big volcano, that's a negative forcing. So there's the one I mentioned before, Pinatubo in 1991, El Chichon 82, Mount Agung 63, and this one back here is Krakatoa in 1883. Right, that was a huge one. If you go back even further, we just passed the 200th anniversary of Tambora, which was an island in Indonesia, which blew up spectacularly about 200 years ago, making a noise that was loud enough to be heard across the world, and killed tens of thousands of people, and cooled the planet for about 2 or 3 years. The Year Without a Summer, there's an excellent book, which is out of print, unfortunately, by Henry Stommel. Some of the oceanographers might know him, who wrote about the Year Without a Summer, basically going back to the old newspaper archives and seeing what was happening to the prices of wheat and the prices of things that were no longer growing. Volcanoes have a really dramatic impact on our climate. Not quite so dramatic. This orange line here, you can see slightly oscillatory. That's the solar forcing. There's some uncertainty about that. You could times it by 2 within the uncertainties, but you can see it's a small term compared to everything else. And then these blue and purple lines are estimates of how important aerosols are. So air pollutions, small particles that end up cooling the atmosphere in the troposphere. So what happens when you put all of these things in as drivers to one of those complex climate models. You get something like this. So this is the model above here. This is the observations, and this is like kind of going through year by year. It's been slightly smoothed so that you don't see all of the variations. But you can see that there's weather. The weather is not correlated from the model to the observations. There's no way to predict weather that far ahead. But what you'll see is that while there's a lot of ups and downs, the pattern that you're seeing as you get towards the end of the 20th century and you get towards the 21st century is actually quite remarkably coherent between the models and the observation. It's warmer in the Arctic than in the tropics. It's warmer in the north than in the south. It's warmer on land than on the ocean. And it's warmer by about the right amount. Models have skill over the 20th century. Not only do they have skill, they allow us to ask questions about what caused those changes. So this is a condensation of those results that I just showed you in the animation. The black line is the data that I showed you before. The blue kind of cloud or envelope is our individual model simulations that have different realizations of the weather, different El Nino events, different warm winters, cold winters, that kind of thing. And they give you a bound of what we expect the weather variability to be, just the internal chaotic dynamics of the system. And you can see the red line is the average of all of those things, and the red line and the black lines meet up quite remarkably. Now we can ask the question, well, what would have happened without us? What if there'd been no increases in greenhouse gases? What if there'd been no increases in air pollution? What if there'd been no deforestation, no ozone hole? Well, then the only things that would have really been changing the climate very much were volcanoes and the sun and the very slow drift in the orbit of the Earth. And what you would have got are these pictures down here, these runs down here. And so here's where we actually ended up. And this is where we would have predicted to have ended up had there not been any anthropogenic or human-caused activity. Now, some of you here are particle physicists, right? Yes? No? Yes, yes. So you're well aware that the threshold for the discovery of the Higgs boson was a 5 sigma event in the 2 experiments that they ran at the Large Hadron Collider. Our current temperatures are over 5 sigma of what we would have expected had there not been any anthropogenic changes. Right? So we are as sure that there has been global warming because of human activities as we are there is a Higgs boson. You know, little contrast there. But we can do better. We can do better because these are complex models and they produce far more diagnostics than just the global mean. Right? So why are these models warming up? These models are warming up because there's a radiative imbalance. There's more energy coming into the system than there is leaving. Where does that energy go? Right? It doesn't go into the atmosphere. The atmosphere doesn't really have that kind of heat capacity. There's some of it goes into melting ice that we saw in the earliest photographs. But actually, that hasn't been very much energy either. Some of it goes into the ground, but the ground is actually quite slow to take up heat. So almost all of the energy that is being caused by the radiative imbalance is going into the ocean. And the rate at which it's going into the ocean is predicted by these models. And the interesting thing is that that quantity in the real world has been a very difficult quantity for people to evaluate. There's been a lot of different changes in how people measure temperature in the ocean. There are a lot of different ways to do it, and stitching these things together in a way that's homogeneous and coherent has been very difficult. And in fact, before we did most of the runs on here, the estimates of this change in the ocean heat content were quite frankly all over the place. Subsequent to doing those experiments, the data people and the observationalists have put together a much better and more coherent data set. And so we can now compare the prediction of the models, and this is really a prediction because we didn't know what the right answer was, with their best now estimates. And so these blue lines are the estimates of what the ocean heat content change was in our models, predicted, and the black lines are what the latest version of the ocean heat content data sets tell us. And this is a real prediction, and does a pretty good job. Oh, gone too far. More real predictions. These were a set of runs. This envelope, again, is the envelope of weather in the system. And here now I'm just focusing on the last 30 or 40 years. We knew what had happened until about 2000, and these runs were done in 2004. But the forecast was from 2000. There was no data there's no observed data in the runs past 2000. And the blue and red lines are the actual temperatures that have occurred. The black line is the estimate of the temperatures averaging over all of those models. And then that's the space of what the weather would be like. So even real-time forecasts over the last 10 or 15 years have been on par. But we need to do better, because the predictions that we're making for 2050, 2080, 2100 are for a planet's climate that is radically different from the one that we know now. It isn't sufficient for us to have credibility and skill at small changes in the climate associated with a volcano or an El Nino event or with a couple of years here or there. We need to have credibility on large climate changes. On climate changes associated, for instance, with the transition from an ice age to the interglacial. Right? The ice age was about 5 degrees colder than today. Right? And 20,000 years ago, this would have been glaciated, right? Does anyone know? There was a glacier here. The terminal moraine goes down the middle of Long Island and ends up in Prospect Park. There's some hummocks there which are also part of the terminal moraine. And so 20,000 years ago, the planet was about 5 degrees colder than it is today. We're predicting that by 2100, we could be 5 degrees warmer, right? So that's one whole ice age unit in the other direction. So we need to know that the models are credible, not just for the small changes, but also for those big changes. And so we spend a lot of time thinking about what we can learn from the Ice Age. What is the data that we have from the Ice Age that would allow us to test whether the models were credible at even predicting such large changes? And so here's an example of what you can do that links the past and the future. So in the tropics, there's an interesting relationship between the temperature over the oceans and the temperature over the land. The land warms faster than the oceans. And in fact, even if you get to equilibrium, the warming over the land is larger than the warming over the oceans. And you can plot that. So all these red dots up there are different models plotting that same ratio for future climates. So they're not all the same, right? So there's some uncertainty in how much of a change there's going to be. But they all fall on a line which tells you that there's something robust about the response to the land and to the ocean. And we can go back in time. We can say to those same models, well, go back to the last glacial maximum. What do you say would have happened then? And you get these blue dots. And interestingly enough, they lie on the same line as the future dots. So future and past are linked because of some key emergent property in the tropics. And now we have the past data, and we can say, well, what happened in the past? What is the measure of this same metric in the past? And that's that blue cross. And you can see that the blue cross lies pretty much right on that same line among the cluster of points that we're using to predict the last glacial maximum. And so we can take a metric that's for the future, we can link it to the past, and we can evaluate how well it did in the past, and then make better predictions of the future. And it works. And so when you have the projections going forward, we have one extra complication, right? The future is unknown. We don't know how the economy will work. We don't know how technology will work. We don't know how society will change. And so we generally run scenarios. And these scenarios vary in their assumptions. So let's run that again. This scenario here, this aggressive mitigation scenario, that assumes that basically this year was the peak year for carbon dioxide emissions, and by the end of the 21st century, we will be sucking carbon dioxide out of the air. So you could also term this the never going to happen scenario. In that case, the temperatures don't go much above where we are, maybe another 0.5 degree or so. Business as usual is pretty much unbridled exploitation of fossil fuel reserves without any concern about emissions. The temperature changes that you get by 2070, 2080, 2100 are well above the 1 ice age unit, right? So this is as warm compared to today as the ice age was cold. The ice age was a completely different planet. This will be a completely different planet. And I don't know exactly how it's going to work out, and I'd rather not test that. And so we end up with something in the middle, where if we make a serious effort, but not an impossible effort, we end up with temperature changes that are on land still about 4 degrees warmer than today. That's still quite a lot. In the Arctic, 4, 5, 6 degrees warmer. That's not compatible with sea ice in the summertime, and it's compatible with a much smaller Greenland ice sheet. The last time the planet was this warm was probably in the Pliocene, about 3 million years ago. And that eventually had sea levels of about 20 meters higher than they are today. So that's about 60 feet. So any of you who visited Steve Schwartz's house, that's way above Steve Schwartz's house. So we're in an odd position, us climate scientists. And the oddness of our position was encapsulated quite well in oh, I completely missed something here. I forgot, I am totally contractually obliged to include a picture of a polar bear in every talk I give. I took this, actually. It was yay close. And I had a good lens. You'll be pleased to know. People care about polar bears. They're cuddly but not nice animals. And they're going to be quite affected by the change in sea ice. I mean, there's very little question about that. But some of the bigger impacts that we're going to see are going to be associated with creatures that are much less cuddly looking. People know what these are? Anybody? Pine bark beetles. And so these little critters don't look like much. But if any of you have been to the Rocky Mountains any time in the last few years, or up to BC or up to Alaska, you will notice that there are huge swaths of forest that are just totally brown. Not just one hillside, hillside after hillside after hillside. The connection between that and climate change is that these creatures, to survive the winter, they grow, and there's about a 6-week period where they build up reserves of antifreeze. And once they have those reserves of antifreeze, they can survive, down to minus 30, minus 40 degrees. But if there's a cold snap while they're growing, kind of like November, early December, they don't have enough antifreeze and it kills them in their tracks. What's happened in the last 20 or 30 years is that those cold snaps are not happening as much. And so more of these beetles are surviving till they have enough antifreeze to survive the full winter and are breeding much faster in the spring. That has devastating impacts. It turns trees that look like this into trees that look like that. And that has potential impacts on things like forest fires and other ecosystem impacts as well. Those things are not very predictable. We are not as good at predicting ecosystem response as we are to predicting temperature changes or heat waves or rainfall pattern changes. And so this is where we get to. So Sherwood Rowland was the discoverer of the chemistry of ozone depletion in 1974 with his colleague Mario Molina. And he became an advocate for doing something about CFCs. He became a champion for the Montreal Protocols. And he gave this statement in an interview in the New Yorker, which really encapsulates kind of where I and other people in my field find themselves. And his statement was this: what's the use of having developed a science well enough to make predictions if, in the end, all we're willing to do is wait for them to come true? And that's tricky because, we're scientists, right? We want our understanding to be validated. We want to feel that we have wrestled something from the real world and presented it to our colleagues and our communities in the world and say, look, we have learned something. We can predict what's going to happen in the future. But when we do, we predict something that is not nice, that is going to be very disruptive. And it's going to be disruptive in ways that we don't even imagine. And so what do we do? I'm open to suggestions. What do we do? So we talk about this. I talk to groups like this. I write books. I talk more about it. But in the end, there's no end. There's just this, and we have to deal with this. And we can get excited about the individual bits of science. I'm writing a paper that I think is very exciting. I'm writing a proposal to work on stuff that I think is very interesting. I'm working with great young people who are really dedicated to wrestling more information out of the real world and out of models and presenting it to their communities in the world. But at the back of my mind, there's always this. So thank you very much.
A perfect end to your talk. As chair, I ask the privilege of the first question, which I will ask of the audience. There have been discussions in the lecture committee about finding a speaker. A candidate's been found who would give a talk telling scientists how to talk to the general public about climate change. Question, would anyone come? Or how many would come? So if I have a quick show of hands, then...
4 people would come. That's good.
Thank you.
You're welcome.
And now for the audience, we are open to questions for the speaker.
Yes.
Could you tell us something on how you measure the temperature of the Earth? We know how to establish the trickle point of water within accuracy, but we are talking here about vast expanse and tenths of a degree. This is optical, then you need to know the optical properties of the surfaces.
No. Okay, so the measurements that I showed you there for the global warming, they come from surface in situ measurements. So they're from weather stations, they're from ocean buoys, they're from ships of passage, they're from floating sensors in the ocean. The reason why we can do this to such accuracy is that the radius of influence, the autocorrelation scale for temperature anomalies on a monthly time scale is actually quite large. So if I'm here in Brookhaven and the temperature is 2 degrees warmer than normal, then in New York City it's also about 2 degrees warmer than normal. And in fact, I can make a prediction for what the temperature change is in Montreal or in Philadelphia. The scale of those temperature anomalies on a monthly basis are actually almost 1,000 kilometers. And so you don't actually need that many temperature points to make a good estimate of the surface of the Earth. Somebody estimated that if you had 60 good data sets, you'd be able to estimate the temperature of the hemisphere to within less than 1/10 of a degree. But we have many more than 60. We have something like 60,000. And so it's a very oversampled field, and you can take independent and totally separate subsets of that, and they all give you the same answer. So we have good error measurements on that. We have a good understanding of what the errors are, and that is actually an accurate measurement of how the temperatures have changed.
But I worry about the environment that the temperature sensor sees during 20 years. When
Yes.
at one time you have forests and then you have buildings.
Yes.
I don't see how you compensate for this.
Because you have 60,000 temperature sensors, some of which are having. So you don't think that measuring many things independently is going to reduce your error?
A thermometer that
Yes.
hangs from a tree, and at one time it sees grass.
No. So at a local single station, you're absolutely correct. There's all sorts of things that can get in the way. Somebody builds a garage. Somebody moves the sensor from the roof to the garden. That sensor gets moved to the airport. All of those things create inhomogeneities in that data set, but they don't all happen at the same time. Right? That one moved to the airport, but all of these ones around it didn't. And because the scale of the temperature anomalies is in the hundreds of kilometers, we can detect inhomogeneities actually quite well. And so we can correct for those kinds of things, and we can throw out stuff that's too contaminated. And there's still enough good data for us to be able to make these estimates with some precision. Oh, yes. So these come from people who are working with what are called integrated assessment models. That's not our group, but you're putting in inputs like the UN population forecasts. You're putting in inputs associated with technology change. You're trying to make things coherent, that if the population goes up and they need food, then you have to chop down forests. The forests give off carbon. They also, so you're trying to make a coherent, plausible storyline for how things might happen. They're not real predictions in the sense that this is what's going to happen, but they are supposed to be coherent storylines for what might happen. For our purposes, what we really want is, well, what's the minimum that you could possibly have, and what's the maximum that you could possibly have, and hopefully you will end up somewhere in the middle.
I think after sort of 1700, it's clear how you're getting the data. Can you give us a brief sketch of what the most important way that you determine things prior to 1700?
So it depends very much on the time scale. So the question is, like, how do you get data before the instrumental period, right? So if you go back to the last ice age, you have a lot of geochemical measurements, isotopes in carbonates, in cave records, in foraminifera, small single-cellular organisms in ocean mud, oxygen isotopes in ice cores in Greenland and Antarctica and in Tibet, and in the Andes and in the Rockies. You have pollen from bogs and things, so you can see where the ecotones kind of move to, and you can use that to infer temperature. We have ice moraines, so we have an idea where the ice was, and that gives us an idea of what the temperature was at those locations as well. Changes in ecosystems, you know, the Amazon kind of switched to a savanna-like situation then. For the period that's more close, where we want to have like higher resolution information, tree rings are used, high resolution ice cores, high resolution cave records, lake records that evolved. There's a lot of information there. It's a bit of a hodgepodge, and putting it together is more fraught than putting together the instrumental record. You know, you can see over the last 1,000 years, you can see the broad sweep of things. You can see, for instance, the big cooling after Tambora. You can see that in the tree rings. You can see that in these records. You can see the cooling in the kind of late 17th century, possibly associated with volcanoes again, but also possibly associated with a solar minimum. And you can see that in these records. And then before that, it was slightly warmer. But you don't get a huge, the further back you go, you know, the more opaque it gets. The Ice Age is interesting because it's opaque there as well, but the signal is much larger. So in fact, the signal to noise is not that different than it is in the 20th century. No, aggressive really means we have to invent by about 2070 a global network of carbon dioxide sucking machines and burying it in unleakable reservoirs. Neither of which seem particularly plausible at this point, but who knows? And then everything has to be renewable by kind of 2050, and we need to be down to about 80% of emissions by then. That's a tall order.
So there was a discussion, I guess, last year about the issue that we've seen no heating for 10 years, which is actually quite true.
Right.
And there was some explanation that it was in the ocean to show some models that predicted the heating of the ocean. Do we understand that effect now? So
this might be something that you see in your field as well. You know, sometimes something happens and like it's a big deal, and then people think about it, and then they come up with far more explanations than you actually need. And so we're in that situation with what's been going on over the last 10 years. And there's two ways to think about this. So if you draw a, let me go back a couple of slides and. There we go. Where was it? Yeah. So this is what you're referring to. You know, so if I draw a line from here to here, it looks flatter than the line that I would have drawn from there to there. The very interesting thing is if I draw a line from here to here, and I calculate the least squares trend, not including 1998, which was a real outlier, and I project it forward, it ends up exactly here, right? So the evidence that there's been a change in the long-term trend is small. Now, but you can ask the question, well, you know, if I just take the short-term thing, what's been going on there, right? You know, what causes, you know, any particular short-term period to have a larger or a smaller trend? And those are interesting questions. So a lot of what you're seeing here, this is a big El Nino event. This was a big La Nina event, this one as well. And this was a small El Nino, and we're kind of moving into a small El Nino at this point here. So changes in the Pacific Ocean are a big part of what's been going on. Now, there's also been a couple of other things going on. So solar cycles, there was a solar minimum in 2008-9, which was actually deeper than all of the solar minimums that we'd seen previously in the satellite record. And the solar maximum that we've kind of come up to since has not been as large as the last solar maximum in 2002. And so there's a potential impact there of solar variability. There's also a potential impact of small volcanoes. So We've had a lot of small volcanoes, nothing like Pinatubo, but it's conceivable that they have enough of an effect to kind of suppress things just a little. And so you have like 3 or 4 things that La Niña transition, the volcanoes and the solar, and possible changes in tropospheric aerosols associated with the switch from North America and European aerosols to Chinese and Indian aerosols, which might have a different impact because of where they are located. You can throw that into the mix as well. And in fact, you have more than enough reasons to explain what's been going on. But my feeling is that the long-term change really hasn't changed.
But are these effects included in the grey band?
No. So in the grey band, remember this is a forecast from 2000, right? The grey band did not have the dip in the solar. It did not have the small volcanoes that went off post-2000. And it doesn't have a very good estimate of what's been going on with aerosol emissions in Asia. So there is some reason to think that this is slightly large, slightly steeper than it should have been in the real world. And if we redo this with better emission data sets and with better forcings, I think we'll see something that looks a little bit closer to what we actually saw in the real world.
Is that ongoing right now?
That's ongoing.
One more question. Yes. You've done a very elegant job of, a very convincing job of painting a very bleak picture. And so I would argue that you shouted fire at the top of your lungs. I think the audience has heard it, I think, before.
Right.
So has anyone done, any people like sociologists or anyone? So if you say there's a fire, I've got 2 options. I can go find a fire extinguisher, I can run out of the building.
Yes.
Are the people who are saying, if we want to translate the reduction in carbon emissions, what does that mean? What are our choices for doing that?
Right.
Because a person needs a certain life. Does it mean we're all going to have to live in houses that are, say, 200 square feet instead of 4,000 square feet? Is anyone addressing that? Because I think if you present people with options, you're probably likely to get a lot better more desirable end result. Maybe the politicians don't like this because, it's too scary.
Yeah. So you're a scientific audience, and I take that into account. If I'm talking to more of a general public audience, you try and end on a slightly less bleak note. People have, of course, looked at what needs to happen in order to be on any of those paths. The most important thing that needs to happen is that you need to have a carbon price. Because until there is a price that is not zero for putting carbon dioxide into the atmosphere, people are going to continue to do it. And people are not going to devote the engineering and technical and design chops needed to get it. Well,
about the lifestyle for the individual, not how to...
So you're not going to solve this. This problem is not going to be solved by everybody buying a Prius, right? Or a Tesla Model S, which is a much nicer car. So I have these discussions with other scientists. So there's a number of scientists who spend a lot of their time telling people that they should go home, reduce their carbon footprint, and feel good about themselves. But that makes this problem one of personal choice, as if we personally chose this situation to arise. We did not. Right? This is not the same as you choosing to smoke or not smoke, and then cutting your risks by doing something that affects your life. I don't think that people cutting their carbon emissions is a bad idea. I don't think that people cycling instead of driving is a bad idea. I don't think people having smaller houses that are better insulated and more efficient appliances are bad ideas. I think all of those things are good. But absent a sustainable and wide-ranging shift at the top, none of those things are going to make any difference at all, right? So, the last time I gave a talk, I was in Vancouver, and And somebody asked me something very similar. So, should you be telling us, like, we should go out there and reduce our emissions and never fly again? And I said, well, I flew here. Would you not have had me do that? And they were a very polite audience, and they all said, no, of course you should have come, of course you should have come. But now, that's a puzzle, right? So, there are a lot of benefits of travel, right? Meeting different people, getting different ideas about how things can be done. The more that we spend in one community, the more we think that that's the only way that we can live our lives. And the more that we travel, the more that we meet people from very different parts of the world with very different ideas about how we can live our lives, the more our minds expand as to the possibilities for how we can live our lives. I think travel is one of the greatest things that we've been able to do in the 20th century and 21st century. Now, that puts me in a very odd position, right? Because my carbon footprint, because of travel commitments that I have, completely overwhelm the fact that I don't own a car, that I live in a small one-bedroom condo, that I have efficient appliances, that we have solar panels on the roof, and that I walk to work. None of that matters, okay? So it would be the height of hypocrisy for me to tell everybody else that they should reduce their carbon footprint while not really attending to my own. And so I've thought about this quite a lot. And the reason why I don't tell people to go out and reduce their carbon footprint, though I don't think it's a bad idea, is because that isn't the issue. It is not a personal choice issue. It is a societal decision issue. So if people ask me, what is it that you should do as an individual to make a difference here? The answer is to influence the people who make bigger decisions than you. And whether that's telling Long Island Power or Con Ed that you want to buy renewable energy, or whether it's voting for a politician that understands that this needs to be a sustainable conversation that needs to go beyond the next electoral cycle and beyond the next presidential campaign, and in fact it needs to be continued for another 20 or 30 years. Those are all good things to do. And I think in the end, they're going to be the better things to do than just, taking the bus because you feel good about your carbon footprint.